Dun 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 dun.
Hello, welcome back. Uh, this is an important video about thinking about our answer for a plate. Now, it's not that I have an obsession with the moment of inertia for a plate, but when we have gotten to an answer, it's good to think about it. Sometimes to even think, could it have been anything else? Is there anything else it could have been? So here, the answer for a plate, which hopefully you should have gotten, is 1/12 mass times length squared plus width squared. Let's think about it from three perspectives. Let's think about it from a units perspective, a symmetry perspective, and a limits perspective. So obviously the units of this are okay. This is kilograms for the mass, and then meters squared for the L squared plus W squared. So like what else that has the same units could we have put here? Like how about mass times length cubed plus the width, or something like that. Like here, that's got to be wrong from a units standpoint. Okay, so I could think of a lot of wrong answers that wouldn't work from units perspective. I mean, to make the units work, we need to have something that has units of mass, kilograms, and then multiplied by something that has a distance squared. So let's see if we can think of some of those options. Like how about something that does work for that, like mass times length to the 1/2 power times width to the 3/2 power. Times some constant. Suppose we thought this was our moment of inertia. We thought this is our answer. Our moment of inertia equals mass times length to the 1/2 power times width to the 3/2 power. This thing would have units of meters squared times kilograms, because the mass would be kilograms. And here the K is just some unitless factor out in front. So this would have the right units, but this would be treating the length and the width differently. We're trying to find the moment of inertia about its center. Surely it wouldn't matter if I switched my perspective and called this length and that width. Or if I took your piece of paper or your computer screen and twisted it 90 degrees. I don't think this problem is able to, like, because we're not finding the. It's not like we're This is a difference in the polar moment of inertia versus the when we were bending beams and strength of materials, the area moment of inertia. Here, this is the polar moment of inertia, so it shouldn't matter these two dimensions, length and width. It should be symmetrical between those two. So anything that's not symmetrical between length and width, where the two can't be interchanged, has got to be wrong. So we could rule out something like that. Even though the units were okay, we could rule it out because it wasn't treating the length and the width the same. And finally, how about something that does treat the length and the width the same? Like how about some constant times the mass times the length times W? I think that might have been a reasonable guess. It's got the right units, and it treats length and width on equal footing. So it meets the first two criteria. But according to this formula, if the length is really, really small, so if the length goes to 0, then our moment of inertia would also go to 0. So if the length goes to 0, the moment of inertia goes to 0. And we know that's wrong, because we know that if the length goes to 0, this basically becomes the shape of a thin rod. And we know for a thin rod that the correct formula for the moment of inertia is 1/12 mass times the length squared. Actually, I should have written as the width goes to 0. I switched my symbols on my picture to make an earlier point. So let me just change that back. So as the width goes to 0, there's my length and width. We know the formula should go to 1/12 mass times length squared, which according to this formula up here, this would be saying that it goes to 0, which would have to be wrong. So I need some formula that when the width becomes close to 0, we get 1/2 times the mass, or excuse me, 1/12 times the mass times the length squared. And so you can think maybe I could have just guessed it. Could it have been anything else than this answer? Times some constant. So this way, as the width goes to 0, you get something times mass times length squared. In fact, this also, by looking at the limit, we can see that that constant has to be 1/12. And likewise, if I make it really thin the other way, so if I make it a really thin rod this way, the formula gives me 1/12 times the mass times the width squared, which is also correct. So I think we can see, by thinking about it, this is what the formula had to be. And in fact, I just, maybe as a fun question, I challenge you to see if you can come up with another answer that fits all three of these criteria, has the right units, is symmetrical, and behaves appropriately if you set either the width or the length